All right, friends, happy Friday. Welcome back to everybody. Last time we were talking about adding hydride equivalents to carbonyl compounds. And we mentioned at the very end that when you take lithium aluminum hydride and react it with an acid chloride or an ester, that you add one equivalent of hydride to get the aldehyde, and then it reacts again, adding another equivalent of hydride to the aldehyde to get the primary alcohol, okay? And we showed you the mechanism of that, and it's probably a memorized detail as to why lithium aluminum hydride can't stop at the aldehyde. But your text rationalizes it with the high reactivity of the lithium aluminum hydride. There are two other reactions we didn't discuss last time. I don't care that you know the mechanism of these reactions. I just want you to be aware of them, that you can actually use the straight carboxylic acid and go and use lithium aluminum hydride to get the alcohol. I don't know that there's a lot of people that do this synthetically, but your text mentions it, and I'm sort of worried that you might encounter it at some point in your future standardized exams for those of you who have MCAT or DAT in their future. Similarly, this amide functional group can be reduced, though not to the alcohol. It actually gets reduced to the corresponding amine, where it looks like you just basically replaced both carbon-oxygen bonds with carbon-hydrogen bonds. The mechanism of that reaction is shown in your text, but I don't care that you know it, and we're not going to talk about it. Just be aware that these two reactions are possibilities. All right, so the question to ask at this point is, what if we wanted to reduce an acid chloride or an ester to the aldehyde and not go all the way to the alcohol? So there are two reagents that can do this, stopping at the aldehyde. I'm going to talk about both of them because your text does, and you'll see them in practice problems. As for our purposes, we're going to assume that you can use them interchangeably. We're not going to necessarily worry about the differences between the two. The first one has a name that is horrible to say, not because it's offensive, but just long. So this is lithium tri-tert-butoxy aluminum hydride. Unlike lithium aluminum hydride, you have only one aluminum hydrogen bond, and the rest of the three groups are T-butoxy groups. You still have a negative charge, formal charge on aluminum. There's still partial negative charge on this hydrogen, but the electron withdrawing nature of these oxygens, because of their electronegativity, pulls electron density away from the hydride and attenuates or decreases its reactivity. So this is less reactive than lithium aluminum hydride, okay? And therefore, you can take this reagent, which is generally abbreviated like this, OTBU3. You can use this reagent to take an acid chloride or an ester and have it stop at the corresponding aldehyde. Your text generally uses this reagent for acid chlorides and the second reagent I'm going to show you for esters. It never tells you that one goes exclusively with the other, but all the examples show it. We're going to use them. We're going to assume this reagent works well with esters and acid chlorides. All right? So the idea is that you tone down the reactivity and it can stop. The second reagent is called Dibol, which is an abbreviation. Organic chemists sometimes love their acronyms. Not as much as the cell biologists, though, I will tell you that. Let's see. That was well, I'm going to go off about my own frustration. Yes, I'm easily distracted. You'll discover in some biochemistry and biology courses the focus is no longer on the atoms, but rather the overall molecules, and so you'll sometimes see in biochemistry textbooks that this amorphous blob that is named some acronym reacts with this an amorphous blob that is named something else, and the names are derived from history and whatnot, but it's maddening to me who likes to know what the atoms are doing. That being said, I respect and honor all my biochemistry and cell biology colleagues. Okay, have I covered my butt now that I've explained? Okay, Dibal stands for diisobutyl aluminum hydride. It looks like this. It's got aluminum, 2 isobutyl groups. Isobutyl. There we go. And then an aluminum hydrogen bond. Unlike lithium aluminum hydride and triterbutoxy aluminum hydride, this reagent is neutral. Now remember, the thing that makes lithium aluminum hydride and this reagent work is that you've got a negative formal charge on the aluminum, and that makes this hydrogen more nucleophilic, like a hydride. Here, you don't have that going on. So, and your text doesn't explain this other than to say, oh, it's less reactive. There is an explanation for this that's well understood, and I'm just going to show it to you briefly. So what happens when you bring this reagent into the presence of an ester is that the carbonyl oxygen attacks the empty p orbital on the aluminum. Aluminum's from the same column of the periodic table as boron. When it's bonded to 3 things, it's trigonal planar sp2 hybridized, and there's an empty unhybridized p orbital on the aluminum. So oxygen attacks the aluminum, and you get an intermediate that looks like this. The oxygen has a positive formal charge. The aluminum now will have a negative formal charge. And now you're in that situation where the negative formal charge on the aluminum is actually felt mostly on the hydrogen. The hydrogen becomes nucleophilic, and now it can be delivered to the carbonyl carbon. So this is a neat reagent because it's not reactive until it finds its partner, okay, until it finds the ester. The product that you get after that step looks like the familiar tetrahedral intermediate that you get after reduction reactions, except it's not negatively charged because the oxygen is bound to the aluminum. So this is sort of a masked tetrahedral intermediate. Normally, if we were using lithium aluminum hydride, we would be at this stage where we'd have a full negative charge on that oxygen, which would be strong enough to kick off the alkoxide leaving group. That generates the aldehyde, and then that goes on and reacts again. But we never do that here because there's no negative charge on the oxygen. This intermediate is stable until until aqueous workup. What is aqueous workup? That's when you add water, perhaps some buffer after the reaction to neutralize whatever starting materials, whatever reagents are reactive still, and it helps you isolate your product. What happens when this molecule comes into the presence of water is that the oxygen from water replaces the oxygen bonded to aluminum here. That frees up your tetrahedral intermediate, which only at that stage can collapse to kick off the leaving group, and that gives you your aldehyde. And at this stage, you don't go on to react again because the reaction's over. You've already neutralized all the aluminum. I'll show you what the aluminum reagent looks like after this point. You still have those alkyl groups on it, but now you've got an aluminum hydroxide bond, and in some cases another one, but we won't worry about that. And if you want, you can forget that. We're not going to sort of worry about what happens to the aluminum. In any case, the reaction's done at that point. So the trick with Dibal is it's not reactive until it finds the ester, but once it reacts, it masks the tetrahedral intermediate, so you can't kick off the leaving group until you quit the reaction, and then the leaving group falls off. Because of that, the aldehyde, the reagent never sees any aldehyde, and so the aldehyde survives. Okay? Yeah? That's right. The aluminum can't give any more hydrides. It only came with one, and in any case, you never make the aldehyde in the presence of this reagent. Yeah. Okay. So those are your strategies. It's nice to be able to have different reagents that allow you to take the same starting material, either this acid chloride or this ester, and end up with the aldehyde instead of the alcohol. Okay, so that sort of ends what we're doing with adding hydride equivalents to carbonyl compounds. Whoops, now, okay, it looks like we're good. We're now going to talk about using carbanion-like nucleophiles. What is a carbanion? Well, a carbanion is a negatively charged carbon. But as with hydride, remember we said we're never going to use hydride by itself. It needs to be delivered. The same thing is pretty true with the carbanion-based nucleophiles. So a typical sp3 carbon-hydrogen bond has a pKa of around 50, which is exceedingly not acidic. What that means is the corresponding conjugate base, or the carbanion, is really, really unstable, really, really reactive. So we're going to introduce a new class of reagents that we're going to use as carriers or deliverers of carbanions. These reagents in general involve bonds between carbon and a metal, and so they are called organometallic reagents. There are many organometallic reagents, but we're going to introduce just 3 today. The first is called an organolithium reagent. And this reagent has a bond between carbon and lithium. Now that you're used to thinking of lithium as a metal, and it is, so that's fine. But you may not be used to seeing metals in covalent bonds. Nevertheless, you can do the analysis, and there's a fair amount of covalent character to that carbon-lithium bond. We're going to think about this reagent as though it were the carbanion with lithium just as a spectator counterion. That picture will be good enough for this class. In reality, reality is a little bit more complicated. For example, lithium can be bonded to more than one carbon, and sometimes you get extended networks of lithiums and carbons bonded together. I mean, that should sort of make you feel kind of weird. And then sometimes we take 2 of these and we spin that around, and then we put it there, and then we make a cube. So it just gets worse and worse. And there are people that study this, but for our purposes, we're going to be fine thinking of it as just the carbanion. Okay? There's another reagent called the Grignard reagent, and we're going to use Grignard and organolithium reagents basically interchangeably. They're going to have similar reactivity. So here is the structure of a Grignard reagent. It involves, instead of lithium, it involves magnesium. Now, magnesium comes from the second row of the periodic table, so magnesium ion should have +2 charge, which means that it can't, that in addition to being bonded to a carbanion-like molecule, it needs another negative charge as well, and that's the Br. These bonds do have some covalent character, but as with the organolithium reagent, we're going to think of this as though it were the carbanion, then Mg2+, and then Br- as spectator counterions. Reality is more complicated than that. As with the organolithium reagents, some of these reagents can aggregate in larger assemblies. Sometimes the magnesium is bonded to 2 alkyl groups instead of 1, but we're going to think of it as reacting just as a single carbon ion. All right. Why do we have 2 different reagents that we're going to use basically interchangeably? Probably for historical reasons, and probably because some of you are going to make this reagent in 353. There's a Grignard reaction in 353, and it's kind of cool when you make the reagent. It's a Pepto-Bismol pink type color, and color changes are amusing, so maybe we do that. The final class of reagents that we're going to see, organometallic reagents, are called cuprates. This involves copper at the +1 oxidation state bonded to 2 different alkyl groups. There's a negative charge on the copper, and then you generally have lithium as the counter ion. But again, we're going to think of this as though it were 2 alkyl groups, a copper and a lithium. Now we'll see that cuprates have different reactivity than organolithium reagents and Grignard reagents. The reason for that, your text doesn't give you. There is a reason. It has to do with the something called hard-soft nucleophile or hard-soft acid-base theory, which is something that's appropriate for an advanced OChem class, but I don't actually even understand it that well, so we won't talk about that. Your text rationalizes this by saying that the electronegativity difference between carbon and copper is not as great, and so this bond is less polarized. But we'll see cuprates are unique, and they do some unique things. Preparing these reagents is pretty easy. You can do that from very simple starting materials. So you can take the alkyl halide and you add lithium metal at the 0 oxidation state. You actually need 2 atoms of lithium for every molecule, for 2 moles of lithium for every mole of alkyl halide, and that generates the organolithium reagent. The mechanism for that involves electron transfer in different steps, and we won't worry about it. Similarly, you can use an alkyl halide and then magnesium metal at the 0 oxidation state, and that will make the Grignard reagent. And this is what you will do in 353. I think you actually take your starting material and solvent, and then you add magnesium metal strips, and then you stir it and heat it and watch the Grignard reagent form. The cuprates you actually get once you've made an organolithium reagent. You take that and you add copper iodide. You generally need 2 equivalents of organolithium reagent per copper iodide, and that gives you the cuprate. Okay. So let's just sort of talk about the different reactivity of these 2 classes, right? The cuprates versus the organolithiums and the Grignards. First, we're thinking of all of them as carbanions, so they're all sensitive to acidic conditions. You're not going to use water as a solvent for these things. You're not going to want there to be acidic protons in your starting materials because, as you would expect, these are really strong bases, and if you have an acidic proton at all, what's going to happen is you're going to rip the proton off water, and then your nucleophile is destroyed and your reaction is done. So though we don't typically worry about what solvents we're going to use in this class, that's a detail that's important for those actually doing the chemistry, but we can sort of neglect. We're going to use solvents that don't have acidic protons. This issue will come up again at the end of this chapter, which we'll probably get to next time. All right, so let's talk about their different reactivity. First, we'll see that there's a class of molecules called alpha-beta unsaturated carbonyl compounds that are reactive not only at the carbonyl carbon, but also at the beta carbon. And the reason for this is because of conjugation. Now, you guys did conjugation and dienes in 351. So hopefully you can see that this pi bond is conjugated to the carbon-oxygen pi bond. And just as we've learned previously that the carbonyl carbon is the electrophilic part of a carbonyl, when you have this alpha-beta unsaturation, you can actually draw a resonance structure where the positive charge is on the beta carbon. So you would expect that beta carbon to be somewhat electrophilic, and it is, all right? If you use an organolithium reagent or a Grignard reagent with this alpha-beta unsaturated carbonyl compound, you attack at the carbonyl carbon. All right, so here's the group that we added, right? And sometimes this process is called 1,2 addition because the things that got added to the carbonyl, the alkyl group, and then in the aqueous workup step, protonating the oxygen, were added to the first and second positions of this conjugated system. A lot of people don't call it 1,2 addition, but some people do, and your text mentions that. So we'll see that organolithiums and Grignards will attack the carbonyl carbon, attack the pi star at the carbonyl carbon. We'll get a familiar tetrahedral intermediate, which will be protonated in a subsequent step. Drawing this in terms of a mechanism is easy. We just, as we did with lithium aluminum hydride, we take the electrons in this carbon-lithium bond, we have them move with the carbon directly being handed off to the carbonyl carbon. That gives us the tetrahedral intermediate that looks like this. And then when we do the aqueous workup step, we pick up a proton from water, and that gives us our product. Okay? That's what Grignard reagents or organolithium reagents do when they encounter a ketone, an alpha-beta unsaturated carbonyl compound. What about cuprates? What do they do? Well, let's take the corresponding cuprate and react it with our alpha-beta unsaturated carbonyl compound starting material. And the product here is perhaps unexpected. The alkyl group adds to the beta carbon. Carbonyl carbon, alpha carbon, beta carbon. Carbonyl carbon, alpha carbon, beta carbon. Here is the new bond that we make. And sometimes people call this 1,4 addition. It's not at all clear right now why it's 1,4 addition. We know that we have 4 atoms in this conjugated system, and we know that we made a bond between the alkyl group on the cuprate and the beta carbon. But what about the 4? Where does that come from? It's kind of dumb, but to see it, you have to see the mechanism. But any questions about what so far? The reactivity patterns are different for cuprates versus alpha-beta unsaturated carbonyl compounds. Yeah? Draw the mechanism for the second one. Yes. Yeah. So, oops. So I'll show it maybe a couple of ways to help you understand what's going on. One of the ways is simply to have the electrons in the carbon-copper bond leave and be handed off directly to the beta carbon. If we stopped there, we would have too many bonds to carbon. So we have to move this pi bond over between the alpha and the carbonyl carbon, and then we have to also break the carbon-oxygen pi bond. Alternatively, you can draw the resonance structure of the alpha-beta unsaturated carbonyl compound that puts a positive charge on the beta carbon, and then you can show attacking the beta carbon directly. Okay? This picture should help you see why the beta carbon is reactive in the first place. And then really these arrows are just to get to this resonance structure. All right? So the intermediate that we have has our new alkyl group attached to the beta carbon. There's now a double bond between alpha and carbonyl carbons, and we've got a negatively charged oxygen. And then this negatively charged oxygen in aqueous workup gets protonated by water. And that gives you this alcohol. Just to keep track of things, here is the alkyl group we added to the beta carbon, and here is the new bond that we made. And if you look at what we've added to this molecule, we added the alkyl group on atom 4, and we added the hydrogen on atom 1. So that's why this is called a 1,4 addition. Now, you'll notice that this is not the product that I drew. These two are isomers of each other. They differ only in the location of a pi bond and a hydrogen. Notice here the hydrogen's on the alpha carbon, whereas here the hydrogen's on the oxygen. Notice here the pi bond's between carbon and oxygen, whereas here the pi bond's between carbon and carbon. Those are isomers of each other, a special kind of isomer called a tautomer. You maybe last semester did you talk about tautomerization-ish? Okay, so that's all that happens here is rapid tautomerization to give you the more stable carbonyl compound. The way that works, honestly, is you just remove this proton to get back here, and then these electrons kick down, and you pick up a proton on the alpha carbon. And for our purposes, I don't care if you want to I'm concerned that some of you are going to look at this and think, oh, these two things are happening at the same time. So what we're going to do here is copy this. People hate it when I copy things because you can't do that on your paper. Haha, suckers. But yeah, the way this works is I don't care if you want to show going directly from here to the actual ketone product by protonating on the alpha carbon, that's fine too. Yeah?
So with the cuprates, it forms an aldehyde, not an alcohol usually?
So the cuprate, if you have an alpha-beta unsaturated carbonyl compound, isn't going to add at position 2, it's going to add at position 4. In the product from the cuprate, notice the ketone is still intact. Whereas for the organolithium or Grignard reagent, the ketone's gone, but the double bond is still intact.
So the organolithium and the Grignard are more reactive, so they go all the way to alcohol, but the cuprate usually ends up ketone.
So what you just said, the question is, does the organolithium and the Grignard go all the way to the alcohol, whereas the cuprate can stop at the ketone or the aldehyde? We are going to talk about that, but this is a different situation. Your text does talk about that, but we're jumping ahead a little bit to the reactivity of this ketone, which is not just a regular ketone. It has this conjugated double bond. And so the first way that cuprates are different from organolithium reagents is that organolithium reagents and Grignards will add to the carbonyl compound, whereas cuprates will add to the beta carbon. But anytime you have the ability to take the same starting material and generate two pretty different products with just two different reagents, that's pretty powerful. That ability to generate diversities of structure is important in the pharmaceutical industry, where you often, in developing a new medicine, want to make as many possibilities as you can, test them all, and find the one that works. So having methods to do stuff is important. All right, go ahead. Is the enol here or the ketone more favorable? The ketone. Carbon-oxygen pi bonds are more stable than carbon-carbon pi bonds. Yeah. Okay, yes?
Is it worth discussing why they add, like, that one can only add to the four position, I wonder if that kind of beyond?
Yeah, it's a great question. Why do these reagents add at 2, or carbonyl carbon, whereas the cuprate adds at carbon 4? The difference has to do with the fact that cuprates are soft nucleophiles, whereas the organolithium and Grignard reagents are harder nucleophiles. But that's hand-waving at this point, because we haven't talked about that kind of hard-soft acid-base theory. So that's a memorized detail, I think, at this point. Yeah. Okay. Second set of memorized details with organolithiums and cuprates is how they react with carboxylic acid derivatives. So we will see that if you have an ester or an acid chloride, and you react it with an organolithium reagent or a Grignard reagent, followed by aqueous workup, your product is a tertiary alcohol where you have two of the same thing attached to what used to be the carbonyl carbon. And the reason for this, if we were to show a mechanism of this reaction like this, might be, let's say we're using this ester and then this organolithium reagent. The mechanism will involve handoff of the carbanion equivalent to the carbonyl carbon, to the pi star, thereby breaking the carbon-oxygen pi bond. You get this tetrahedral intermediate, and then you ask, are there any leaving groups that the negatively charged oxygen is strong enough to push off? The answer is yes. A negatively charged oxygen can displace or push off another negatively charged oxygen. So we get, and that's just another way of saying that this reaction is favorable, or at least reasonable, because a negatively charged oxygen here is about as stable as a negatively charged oxygen there. But then the key issue is just that this ketone is itself reactive. It itself has a pi star that the carbanion-like nucleophile can attack. Once that happens, you get the tetrahedral intermediate again, but this time there's no good leaving group on the sp3 hybridized carbon, so you're stuck there until aqueous workup, wherein the negatively charged oxygen picks up a proton from water to give you your tertiary alcohol product. And you can tell that a tertiary alcohol has been made via this method because it will have two of the same thing attached to the tertiary carbon. All right? So that's how organolithiums and Grignards react with acid chlorides or esters. Cuprates do something different. So if instead we took this same starting material, and your text, I think, only reacts cuprates with acid chlorides. We're going to assume, I don't actually know this because I've never done the reaction, but we're going to pretend like this reaction works. It definitely works for acid chlorides. If you find out someday it doesn't work for esters, think of me fondly for oversimplifying to you when it didn't matter, and forgive me for not preparing you for the unlikely event that it will matter in your lives. Okay, so if we take the corresponding cuprate followed by aqueous workup, we get to the same intermediate via the same mechanism. So the first two steps are going to be exactly the same. Oops. What the heck am I doing here? I was going to be general, and then I decided to be specific halfway through. That's kind of irritating. I'm sorry. So you get to the ketone where you've added just one equivalent of your alkyl group, and there you stop. Okay? Why do you stop there? The explanation's not really given to you. Again, it probably has to do with hard soft acid base theory and cuprates being soft nucleophiles, but that's a memorized detail. One key feature of recognizing products from this kind of reaction is the fact that this is a non-symmetric ketone, right? You've got a ketone where two things on either side of it are not the same thing. All right. Yes?
Does this reaction involve the second step where you do aqueous workup, because your result is a ketone, not an alcohol?
Right. You do aqueous workup. The question is, why would you bother? Because you don't have a negative charge to protonate. And the answer is it's probably to quench whatever remaining cuprate reagent is present. Frankly, aqueous workup happens for most organic reactions after you do them, but yeah. Okay. So that's the second way that cuprates and organolithium reagents will differ. Okay? Now, there's a lot of ways you can mix and match with these things, and I'm not going to bother to explain how or why if you take an organolithium reagent and react it with an aldehyde, you get a secondary alcohol. Nor am I going to spend very much time talking about how if you make a stereocenter here, you got to have both varieties because you're adding to a flat carbonyl compound from above or below. The principles that we've learned before follow, and with the exceptions of sort of what we've just talked about, these memorized details, if you understand carbonyl reactivity, you understand nucleophiles attack electrophiles, the results of this sort of just flow out of the analysis. Now, if you're struggling to keep track of it all, I do have a recommendation. One of the things you can do is to try to master reactions in a couple of different ways. The first might be to take a starting material and a reagent and then make yourself predict what the product is. Then for that same reaction, give yourself two additional quizzes. Draw the starting material and the product and ask yourself, what must the reagent have been? Or alternatively, give yourself the reagent and the product and ask yourself, what must the starting material have been? If you can do this, you will know that if you can do this, you'll know that you've mastered this reaction. And this will allow you to answer not only predict products questions, but also synthesis types of questions where you're thinking backwards. So this will make it so that when you see a tertiary alcohol that's got two of the same thing attached to the carbon, you're thinking, oh, I know how I could have got that. All right? So maybe, why not? Let's practice a little bit. Let me ask you, what if I wanted to make this tertiary alcohol? Those benzene rings look sort of sad and sort of neutral. So let's do retrosynthesis. How could I have made that? Actually, let's have you write some stuff down, and I'm going to blank the screen, and I'm going to give you options just like in a, well, you want to see it again now that I blanked the screen. I'm going to write down some options like in a multiple choice test, and then you can see whether your option shows up on the paper or not. Okay, everybody got it? Okay, go. Think backwards. I'm going to write some various options. Okay, you got something written down? Make a commitment, put it on paper. All right, here's your choices. And actually, if we had more time, I would have written some more options. Some of you, when I said multiple choice exams, were thinking, oh good, A versus B, true or false. This is not elementary school anymore. I will sometimes give you options A through J. I would do more, but I think the testing center limits me to like A through J. So in any case, being able to come up with the right answer and then recognize it is important. So what do you think? Of these options, what do you pick? C, that's good. C is in fact the correct answer. What's wrong with A? Yeah, you get the wrong, you get two of one thing, but it's two of the wrong one thing, right? B, what's wrong with that? It's not a carboxylic acid derivative, you're going to get a secondary alcohol. What about D? What's wrong with D? Gives you the ketone. And E, well, E is good, but come on, guess something. Okay, now I want to do, go ahead.
Could you possibly also do it and you put ketone reacting with
Great, so you're asking, could I have started with, say, a ketone, and then reacted it with a Grignard or an organolithium. Yeah, that's perfect. That's fine. Yep. You just have to see if that was one of the options. Ooh, maybe I should write a question where there are multiple right answers and you have to select all of the right answers and none of the wrong answers. I've done that before, actually. You always get partial credit, though. So, all right, I want to ask you a synthesis question. Now I'm gonna draw you an alcohol, and it's a tertiary alcohol, but this time there are 3 different things attached to it. Oh, I used 2 of the same color. That's deceitful. Okay, 3 different things attached. Go ahead.
Professor, do you do negative marking?
Oh, right. Do I do negative marking? No.
So just select them all the time.
So that's, we've got gamers here. So yeah, the idea is, if you have to select all the right answers and none of the wrong answers, but there's no negative marking, that means I just select all of the answers and then I get the questions right. Yeah, try that, see what happens. Okay, so how about this? How could I make it? Let's think retrosynthetically. If I wanted to do this, what would be the problem with it? I get 2 of the benzene rings, right? So, any ideas? Oh, sorry. Okay, fine. 1, 2, 3, 4. Okay, what's wrong with that? I get 2 of the alkyl groups, right? I need 3 different things. So, can you think of something I might do to prevent that? Go ahead.
Do the cuprate reaction first.
All right, let's do the cuprate reaction first, since I've just got used to drawing zigzags with 4 carbons. We'll do that. That would give us the asymmetric ketone, and we would stop there. Then what?
Then do the organolithium.
Do either the Grignard or the organolithium. Either or is fine. Yeah. Perfect. Yeah, you use the different reactivity of these reagents to allow you to add just one thing to the acid chloride to get the ketone, and then a separate thing in the next step to get your tertiary alcohol. And there's more ways than that to do this, but that's using sort of what we've done so far strategically to help you make the right stuff. Okay. Other questions? Let me give you one that's related to the first way in which ketones are different from, or rather cuprates are different from organolithiums and Grignard reagents. I want to make this from a starting material that let's say I have to use this as my starting material, and then I can use anything else. That's a tough one to recognize. It doesn't look like what we've been doing in the sense that it's not an alcohol. And the benzene ring, which we have to use, isn't attached to the carbonyl carbon. They're having more fun than you. So the key is to recognize that you have a carbon-carbon bond at the beta carbon. Okay, did I get your memory going? Actually, what we're going to do is make you stew over this over the whole weekend.